Great. Thank you. I would like to thank Baumeling for giving me an opportunity to speak here. First, I will also apologize for that. I will leave after my talk because I found that I cannot check in. So I have to go with my student to the airport after talk. But if you have any questions, please feel free to email me and we can set up some other chances to discuss more. So today I'm going to talk about nonparametric learning of interaction kernels in interacting particle systems. And this is a joint work with our group at Johns Hopkins with Mauro and his group, and also some of my students. And first, I would like support from Johns Hopkins and from Natural Science Foundation. So let's start with the following problem. The question here is, from ancient times, from this solar system to the flocking birds to the water model on the internet, the question is we can view each of these objects as a particle. So the question here is, what's the law of interaction between the particles? Okay, so for the first one, we have good answers. The early data scientists, including Newton, have already given us some answer there. So we model them by the Newton system, and then we assume the particles interact with each other in pair, and we want to estimate some interaction kernel, this small phi here. We could also call this K, capital K phi, as phi. But here in this talk, I will focus on this radial interaction kernel. But all the rest theory later, we can also do it for non-radial multi-dimensional kernel. So let's come back to this Newton's gravity, the law of gravity. We have this law. This kernel is 1 over r squared. That's the kernel we want. And for the electronics, the particles, we have this Lunar-Jones potential. Okay. So this kernel, we have physics, we have many guidance about how do we get there. Now the question here is, when we move to the flocking birds or people appealing on the internet, how do we model them? Clearly, there's no such a clear rule about what the kernel would be. And it's hard for us to guess any analytic form. Okay. So in this case, since with now recent improvement of technology, we can record many data. Now the question is, can we infer the kernel from data? Okay, so that's the question we want to answer. So now let's put this in a mathematical format. So we're going to consider in this talk, mainly I will demonstrate the idea using the first order system, and I'm adding some noise here. If we put this nu to be 0, there's no diffusion, then we get the ODE system. But we can put the nu non-zero to have noise there. Okay. So in this setting, we are going to have this ODE or SDE, and then this dimension for each particle, this xi, is in dimension RD, and we have n particles. The capital N is the number of particles interacting with each other. So in this case, if this n is finite, like we have finite many particles, then we can see that we can keep track of the trajectory or of all the particles. We can have many different tracks. We can call this M trajectories of particles. Okay. That's the one type of data. And in this case, now from this data, and we can view them as some sample of this high-dimensional process X. And we want to have a statistical learning problem for the estimation of the kernel phi. Okay. So that's the N is finite. This is the statistical learning problem. Okay. And the question here is, also, we know that in many systems, we have a large N. N is very large. And then in this case, it's hard for us to keep track of all particles, all their trajectories. We can observe their ensemble distribution or concentration density of the system. So in this case, then we can have one solution here. We can view them as the mean field solution, the PDE solution. And then in this case, we can view them as on some mesh if we have lower dimension, and we want to estimate the kernel phi from the mean field solution, the PDE solution. So it's an inverse problem for PDE. Okay. So these are two problems. Now we can see the connection now. One is the statistical learning problem with many sample trajectories. One here we have a single PDE solution. We want to estimate the kernel. So that's the problem we want. And now let's put them in some abstract form so that we can see what's actually behind. So let's look at this first equation. We write this as the vector form. We have basically what we have is we put this part the whole bundle together as R phi from this high dimensional RND vector to this this x dot. I'm basically putting this in the differential format. It's one noise. So that's what we want. So now we have data. We can see we can estimate this one, and then we want to estimate with some noise. We want to estimate this operator R phi from this RND to RND. Okay. And similarly for the PDE part, we can put this part as our operator R phi. And in this case, we want from R phi U to F. So this high dimensional vector, this is the function. The R phi is a map from one space to another. So we want to learn this phi in this operator. Okay. So in this case, then we can think about different settings now. In the classical learning setting, we have xi, yi with basically noise division of phi I. And in this, what we have here is kernel learning. We want to learn this uk to fk, which is the noise division r phi uk. And in the operator learning setting, basically we have similar setting. But now in this setting, we learn the operator. We don't worry about the kernel phi. We don't assume the kernel structure. So let's look at this. What do we have here? In the classical learning setting, what we have is we have given each xi, we have the yi is basically local perturbation of the true value. It's local dependence. Okay? And basically, we can view in this setting, we have some kind of good filtering or regularization or interpolation strategy to learn the function phi in the classical learning setting. And now in the learning kernel setting, so given the data uk or like fk here or this high dimensional xt, we have no idea where the value of the phi would be because it depends on the kernel non-locally. So that's the key difference. There's nothing we can do any interpolation. Okay. Now, if we look at higher dimensional with the operator setting, infinite dimensional setting, if we put u as the x-axis now, the horizontal axis, and then this RU essentially is a local perturbation of the operator. It's still like the local dependence, but the difficulty here is dimension is infinite dimensional or high dimensional. So in this sense, the learning kernel, what we are having here is in the middle part of the two. But here, since we assume this kernel structure, we can assume the kernel is low dimensional. We know that many high dimensional problem, there is intrinsic low dimensional structure. Here we assume we know it and we want to find it. So in this setting, we can put ourselves more close to the classical setting, and we can, if we want to start from it, before we go to higher dimension, we can start from lower dimensional structure like the radial kernel, see how far we can go. Okay. So in this setting, then we want to compare with the classical nonparametric learning, especially nonparametric regression, is how do we define a suitable loss function? And then in this case, can we have identifiability as we had before? And do we have the min-max rate of convergence? Okay. So that's the things we want to answer. Well, one key point here is, if we look back for one more slide, we will see this k actually depends on, sorry, I think I should go back. K here, it depends on phi linearly. Okay, that's the key thing I want to emphasize. Since k depends on phi linearly, then this R phi will depend on this phi linearly. The operator depends on phi linearly. That's the important structure we assume. So everything, once we notice this, all what we can do now and next we can do is in regression. So that's where we are going to start with the finite many particles as example to demonstrate this. And then we move to mean field and then come back to learn with a non-local dependence. Okay. So now let's look at the finite dimension particles. Then this is some typical trajectory we would have. This is the one of the Lunar-Jones, deterministic one without noise. And the second one is we have add noise to it, the two different trajectories. And this one is the opinion dynamics, deterministic and stochastic. We can see from these trajectories, we have very limited information about what a kernel would be. Okay? So, but no, we know that it's R phi depends on phi linearly. The natural thing we can do is try to do regression. Left-hand side minus the right-hand side. And that's the MSE or log likelihood if it's SDE. Okay. So then with this, we can see we can continue to do this regression idea. We propose some hypothesis space with basis, and then we do use regression to get it. But the problem here, a few problems there. So first, how do we choose this hypothesis space? What are the basis functions we use? Because we don't know the support of phi. And we need to get that from data. And then once we have it, and then we need to consider about which function space are we doing the learning. Like which function space does this estimator belong to? And then we can analyze convergence in that space. And then we are doing the inversion here. Basically, we have A inverse, the matrix inverse. and then is this well posed? And in the end, if there's the true function phi, is this identifiable? And then if identifiable, can we get some convergence rate? Okay, so that's the theme we want to address in this setting. So to do this, we're going to compare with the classical learning, especially classical nonparametric regression, and see what's the difference. So top part is basically the same. Once we have loss function, they're both quadratic in the function to be learned. This part is f, a classical xi, yi, we get this f. So here we have this kernel phi, we want to estimate it. This part is standard. And now let's go more. So in the classical learning setting, we know the function space for learning, the L2 rho x. Rho is a distribution of x. And identifiability is clear, because in this case, what we have is the conditional expectation give us the unique minimizer of the loss function. And then in that case, if we choose this basis function to be orthonormal in L2, then we get A basically like an identity matrix. The inverse problem is well defined. Everything should be good. And then over there, we have error bound or conversion rate for the estimator. Now coming back to our setting, then what do we have here? So now we have this phi is dependent on pairwise distance. So we can see that we can use the empirical measure to see where we can learn the function. So this rho is empirical, and we get it from data. Beyond this data, basically the inverse problem is ill defined. We don't know where the kernel would be. It's in a nonparametric setting. Okay. And the second one here is, so now can we have something similar as the unique minimizer of the loss function? And that's something to be investigated. And then similarly connected here is, if we choose this basis function property, do we have this A inversion matrix to be well conditioned? So in this case, both these two will be answered by a coercivity condition. Yes, Matt?
Do you assume you observe x dot?
Oh, we don't observe x dot. We approximate derivative. That's noisy.
Do you numerically differentiate?
Yes. Yeah. And in the case of stochastic differential equation with likelihood, we basically also like the difference. Yeah. So in this setting, then can we get the error bound for this estimator in this L2 space? Okay. So what we have here is we assume this condition. We call it coercivity condition. Essentially saying that this inner product, we call it this new inner product on this L2 rho to be this part comes from the loss function. I should say here. Oh, sorry. This part. Sorry, I'm messing up. This part is from this A matrix come from the loss function, the quadratic part. And basically from the quadratic part, from the A matrix, we can define the coercivity condition. So what we need essentially to make this A to be well conditioned, we need this CH is like the smallest eigenvalue of the A matrix. Or in other words, we want the derivative of the loss function to have a lower bound on the L2 rho. Over here, actually, we realize later, we will see later, we cannot get this on L2 rho in general. We have to select some space. It's like what we have in machine learning. We choose some hypothesis space. Mostly we assume them to be compact in some sense. So here, it's hopeful we want to get the L2 rho, but in most cases, as we will see later, we cannot get it. So now, what do we have proved this one for L2 rho? That's the optimal case we want to estimate. We have proved for some kernels, we do have this coercivity condition for a hypothesis space to be L2 rho. That means any kernel in that setting, we can learn it. And there's a coercivity constant is 1/n squared. So let's put a mark here, because we know that we're going to study the case n goes to infinity. That means this one, we don't have the coercivity condition on L2 rho. So this is still open question for general kernels or general systems. And the proof over here is basically come back to a very fundamental undergraduate level problem. Basically write two expectations and see if these have the lower bound. So that's a very simple problem. We can state it very neatly, and then everything goes back to the analysis. So if you're interested, I'm happy to talk more about this. And with this coercivity condition, when we move forward, we do the computation, we can find the following theorem about the convergence of estimator. Basically, we prove that as the data size increases, our estimator will converge at this is the minimax rate, is S over 2S, where this S is the here is the kind of characterize how the hypothesis space is close to the true kernel. And in general, we would assume the true kernel to have the Holder continuity of order S to have this rate. So the smoother your true kernel is, the more likely you get a higher rate. Okay. And with this rate, basically, we also asked Khan's question earlier is how much data we need to get a reasonable accuracy. So that's the convergence result. And here, this n, the dimension of the hypothesis space, have to be adaptive to the regularity of the true kernel as well as the data size. And then the basic idea here is like the classic regression. We don't want to underfit, we don't want to overfit, we want to get a balanced fit. Okay. That's a dimension selection. Okay. And we tested this for different systems. And the following is for the stochastic systems we have. And this shaded part is the empirical L2 rule matter. This is the rule matter. And that's where basically with this rule in this part we have more data to learn the kernel. And go beyond this, the rule will be almost 0. That means when we are selecting basis function, we should not select basis function to be outside of this range because there's no data for it. And the first one is Lunar Jones kernel. What we plotted here is the true kernel along with the standard deviation of 10 different estimators around it. So this one is relatively accurate. And we can see this part, the standard deviation is very large. It's because here we have limited data to estimate it. So in this range, that means we have less confidence of our estimation. But L2 rule-wise, the estimator is still good. And the result give us, for the trajectory prediction, is still accurate. Okay. And we further test the convergence rate for this estimator. With different level of noise, we can get an estimator. In both cases, our convergence rate matches the theoretical slope, which is about 0.41. Basically, we match the rate for the dashed one. That's the optimal rate. Okay. And we also consider this long smooth kernel, which is the opinion dynamics. Basically, this have jump here, piecewise constant with the proper normalization. And we see here in this one, our estimator have large oscillation, especially when this rho is small. So this true kernel is discontinuous. And still, because we're using L2 rule matter, that's the correct matter for it. And we can also get the almost optimal rate for this system. Okay. Okay. So that's for the finite particle system. And then we move on to the mean field equation. And this is the part I think Qianjun have already presented in the poster. I will briefly review it and then come to the key part in comparison with the finite case. So the problem we recall here, what we want here is we have the discrete data for the U at discrete mesh. In the later test, we're going to use only 1D, but here the theory applies for X being higher dimension. Okay. So what we have here, we want to estimate this kernel from this equation. And following the previous structure, what we want to do first, we want to find a good loss function. And in this case, since we know that our data is discrete, to imitate the case that we have using particle approximation, is based on approximate measure, is a measure solution to it. We do not want to get any strong solution. So that rules out the first one. We use left-hand side minus right-hand side. This loss function will basically give us a very bad result because we have the approximate second-order derivative and first-order derivative. And then we go to the other extreme. We want to use them without using any derivative. One quick thing here is we know that this mean field equation is the flow in the Western distance of measures. And then we can think about the free energy over the Western distance. For the free energy, basically, we will quickly realize there's limited information on the kernel because essentially this part is the expectation of the kernel. And we don't have the true kernel. It's hard for us to give us any reasonable estimation. And then the Western distance here in this case, because the U is a measure, and for each kernel, we give a kernel, we can solve for it. And then to do in this case, we have the optimization problem. That means we have to solve this PDE many times, and that's very computationally costly. Okay. Instead, we are going to see next, since we have a trajectory of a solution in time, and then in this case, a probabilistic loss functional basically can give us a least square regression problem. So it's come from here. The loss function is in this format, and this part is the square part is quadratic part. This part is linear on the side, and this part comes from data. And to get here, basically, we come back to this McKean-Vlasov mean field equation for this particle system. And from here, what we get is basically we compute the log likelihood of the process. We get exactly as we have draw here in the loss function without any derivative u. To get rid of the derivative from the diffusion part, we use integrate by parts. So in this setting, we have this loss function without u, without gradient. Actually, even the time derivative here, we can get rid of it because we're doing integration time later. Okay. So that's the advantage of this method. This loss function now is derivative free, and more importantly, since later we want to consider higher dimensional particles, and we can see here this k convoluted u essentially can be written as a conditional expectation of the process. And so in this case, if you have particles approximating the solution, basically everything here, the integral with u or convolution here, everything can be written as expectation. So in the end, if you have higher dimensional particles to represent the u, and we can still use this one for regression. So then we come back to the nonparametric regression. Everything will be the same. We have this identifiability shield function space, and then in this case, slight difference here is when the space mesh goes to 0, where we get a convergence. Okay, and then in this case, the key issue is still is identifiability, and we look at the quadratic form. In this case, we can quickly see that with a radial transformation, we can get this integral form. Basically, this bilinear form in this case, in the operator in the matrix A, is operator LG with the basis. And then what we have, if we want to have a coercivity condition, what we have basically we want this one to be bigger than 0 as before. Now, as we have noticed earlier, as n goes to infinity, we don't have coercivity condition on L2, and we can only hope for some hypothesis space which is compact. We can get the coercivity condition. And come back to identifiability. Essentially, what we are doing, the A inverse B is actually, if we put it in the function space learning setting, we are doing the inversion of this LG operator. This LG operator turns out to be compact, so that means we have a E-opposed inverse problem. Regularization is necessary, and then in this case, we can only learn this function inside the eigenspace where the non-zero eigenvalues of this compact operator. The zero eigenvalue in this direction, we have no information to learn about the true kernel. So that's the key observation here. And another observation here is actually this LG is a self-adjoint or symmetric operator, since it's real valued in the function space. So then this operator defines a reproducing kernel Hilbert space, and that the closure of this HG is the function space that we can learn, we can identify the function. So this gives us a good way to do the regularization, because for this E-opposed problem, the phi d from data often have noise in it. So in this case, the RKHS norm provides us good norm for regularization. We're going to come back to it. We call this norm. This regularization is data adaptive RKHS type regularization. Okay. So with this, and then similar to before, we assume the coercivity condition, assume super regularity of the true kernel, we can get this rate. Now this rate is slightly different from the statistical learning setting now, because we are using numerical integration of the integrals, and because we are having data on the mesh. So then this sampling error will be replaced by numerical error. So the trade-off will be numerical error and the approximation error from the hypothesis space. And the optimal rate we can get by choosing the dimension of hypothesis space properly as before is this rate. It's alpha s over s plus 1. So in this setting, basically, we can see it's similar to what we have in the statistical learning from the color approximation. Okay, and time. So the quick example, I think you have Chenyu already presented. We have 3 cases. We test 3 cases for smooth kernel, and later piecewise constant kernel, and the non-singular kernel. And the main message here is when this kernel is smooth, it's good, and we can get this phi in the satisfying the assumption we have. We can get the almost optimal rate. That's what we can get. And then when the kernel is piecewise linear in this case, then we couldn't get an optimal rate. We get suboptimal rate because the true function is not in the space in our theorem. And then when this kernel is almost singular, basically our theory does not apply at all, and we don't get a good rate. Here the rate is very bad. Okay, but in all cases, The Western distance is quite close. So that also gives us some sense that if we use Western distance to do the optimization, we believe that we will have some trouble to get the unique solution in the optimization part. Okay, so that's the learning kernel mean field equation and the entirely particle systems. I want to take them back to the general setting of the learning kernel operators that we have wrote before. Basically, we view this R5 from U to F, and then get it from data UKFK, and we want to learn the kernel as the example before. And as we can see, and then such kernels happens a lot, especially for these integral kernels or long-local kernels, as long as this F, this data here, depends on the phi long-locally. So we call these learning kernels with non-local dependence. In general, many in the E-oppose inverse problem have this structure. So the question here in this case, we can major question here is if we formulate it as the regression problem, we are doing this inversion of a compact operator here. Now the natural thing we have to do is do the regularization. We have seen various regularizations focusing on tuning the parameters, hyperparameter. But there is another question here is what norm should we use for regularization? And in our study, we basically found that this RKHS norm help us to constrain the search to be in the function space where we can learn the kernel. And then outside of it, basically we know where there's limited information or most noise. So we believe this RKHS regularization would give us a good chance. And in a few tests, we have seen that we can get a consistent rate of convergence as the data mesh refines, regardless of the noise level. So I think that's the one of the potential direction for application of this data adaptive RKHS for regularization. And since this RKHS norm can be applied for higher dimension, we believe it's potentially applicable to higher dimensional kernel if you learn it with a network. Okay, so I think I will summarize here. What we have started with non-parametric learning of internal particles in a finite particle to mean field equations. From there, put in a general setting of learning operators via regression. Basically, in these settings, we propose probability loss functions to make this as a least square regression problem. And we studied identifiability and also studied convergence with the proper function space. And based on this, we introduced a data regularization for E-oppose inverse problem. And there are many inverse future directions. The key question here, fundamental one, is the cursivity condition. As we have seen, if we have cursivity condition, everything reduced to the classical setting, and we have the min-max rate. But without it, it's much harder. And then the question without it, can we get any min-max rate? That's this one. And regarding of these other settings, I want to mention one here because we have Bayesian statistic here. So we can view this regularization as a regularization. And the regularization basically we can view it as a prior. So in that setting, how do we view this data as a prior? Is it in some way good, or do we have any convergent result as Sayan had presented yesterday? Okay, with that, I will stop here. Thank you.